Here's the answers to the last try questions. So I did the substitution over here, and then here's my final answer. So that's what you would check it with. Let's just circle this. The substitution was here. If you get any of them wrong or you're unsure, just pause it and look at the notes and see if you can work your way through them. Here, this one often gets people messed up. Both of these are the U, because we want to end up with secant tan, which is secant. So both of these parts are U, and then the du stuff would be, or the stuff that's left is x and the dx. And then this is linear, so you wouldn't have had to do this substitution if you noticed it. You could have jumped right to the answer. If you notice that that was linear, you say, okay, what's the, 2 is a constant, what's the integral of tan? Integral of tan is ln of secant. Rewrite the argument, divide by 3. So let's put that over there. And that is the answer I got here using the substitution. Okay, the next type is ln and inverse trig. So this is the first time we're going to see a ln itself in the question, or like an inverse trig in the question. There's actually only 2 ways you can do these integrals, or else they can't be solved. So the first way is by substitution, and the second way is a different technique called by parts, which we're going to learn next. So, but for now, I'm just going to set the ln and inverse trig ones up to work by substitution. Okay, so we'll call this type 5, logs and inverse trig. So basically, if there is a ln in the question, then there would need to be the derivative of ln for substitution to work, and that's a 1 over x. So, for example, if I put just a basic one, ln x over x, these x's don't cancel. Ln x is one entity. The x is attached. It needs an argument, and the whole thing is divided by x. So this could also be seen as ln x times 1 over x dx. And for this type, when you see a ln and the derivative of it in the question, you call u the ln, the whole thing. The derivative of ln is 1 over x, and that's what was left over. So du is 1 over x dx, 1 over x dx. So if we rewrite that, we call the ln u the whole thing. And we drop these off, and in their place, du. So this one would be u squared over 2, ln x squared over 2 plus c. Integral of u is u squared over 2. So that's ln. Now, just to remind you how derivatives of logs work, we're only doing the natural log. So how do derivatives of logs work? Well, let's see. The argument goes on the bottom and the derivative of it on top. So that's how that would work. So if we had a question in it, let's say we had the square root of ln of 2x plus 1 all over 2x plus 1. You would call u the ln, the whole ln, of 2x plus 1. The derivative, 2x plus 1, derivative of that is 2. And if you look over here, let's rewrite it. This is times 1 over 2x plus 1. So it's this radical times 1 over 2x plus 1. and we can get that by rearranging. du over 2 is equal to 1 over 2x plus 1 times dx, and that's what we have. So if we rewrite it, we've got a square root here, so root u, we call the inside of that. It's a bracket to a power, so you could also see it as that type. This stuff drops off, and in its place du over 2. Let's bring the half out front. This would be u to the half. Oops, sorry. Okay, so this we call the inside of that bracket u. This whole thing drops off, and in its place du over 2. Bring the half. Rewrite that as u to the half. Add 1 to the exponent. Divide by the same number, plus c. And u was ln of 2x plus 1. And so put a big bracket, ln of 2x plus 1, big bracket, to the 3 over 2. Okay, we often just see ln x. We don't often see the arguments change, but it could be. There's no reason why we couldn't do it that way. We can certainly take the derivative of anything, any ln, and then that appear. You just often see it just with a regular log. Okay. So, we'll do a couple inverse trig examples. So for, let's say, arctan, if we wanted the derivative of arctan, that's 1 over 1 plus x squared. So in the question, if there's an arctan, there also has to be a 1 over 1 plus x squared. And then if there was an arcsine in the question, whoops, and arccos, okay, these are very similar. One's negative, one's positive. Okay, but if any of these were to appear in an integral, like an arctan, it would also have to have this. So an integral, if we had, say, arctan x all squared, it would have to have the 1 over 1 plus x squared, the derivative of it, in it. Same with these. We could say this is just arcsine, oops, of x divided by root 1 minus x squared. That would work. So it has to have that root 1 minus x squared in it. It doesn't have to have the negative, but if it does have an arccos, let's say we had 2 arccos, I'll write it the other way just to remind you that they do mean the same thing. Okay, these will be quite similar. This one has a 2 and this one doesn't, but otherwise it's just the inverse trig divided by the derivative of it. Here we've got the arctan bracket. So let's do these 3. But in all of the cases, if you see that inverse trig, you call that u, and the derivative has to be somewhere else for it to work using this type. So this would be arctan x. The derivative is 1 over 1 plus x squared. And there is a 1 over 1 plus x squared in here. This is arctan x squared, 1 over 1 plus x squared dx. So, and there it is. So this will be u squared, and this whole thing is du. So u cubed over 3 plus c, and u is arctan. Put it in a big bracket, and there we go. You could write the 3 as 1/3. The second one, you let u equal arcsine. The derivative is 1 over root 1 minus x squared. And that's all we have in here. We don't even have a bracket to a power or anything. We've got the 1 over 1 minus x squared dx. Rearrange this. And it's just du. So arc sine x, that whole thing drops off. Oh, sorry. Arc sine is u. U, this whole thing drops off, and du. Integral of u is u squared over 2. And we said u is arc sine. That's pretty much it for these types. So the third one that's up there, that's going to be the one you'll try. I'll fill in the blanks, but you give it a try. You're going to call u arc cos, and then rearrange the differential to get the integral. Okay, and we'll stop there and you give that one a try, and then we'll start the next type.